Okay, so the last speaker for this parallel session is Andrei Constantin from the University of Oxford, who will tell us about computation of fermion masses and mixing in geometric string compactifications.
Thank you, Kostas, for the introduction and for the invitation. The title of my talk refers to some work which appeared at the beginning of the year, but I decided to embed this result into the larger effort of string model building and to discuss the mathematical and computational complexities that come with that. So that will take me into a discussion of work done in collaboration with Steve Abel, Callum Brodie, Kit Fraser Taliente, James Gray, Thomas Harbin, Luca Mucicati, Andrew Lucas, Bert Overton, and Fabian Drule over the last couple of years. So the main theme of my talk is the problem of connecting string theory to particle physics. And this is not a new problem, it's an old problem, and in principle the connection between the two has been done almost 4 decades ago. But the practicalities of actually realizing this connection, I believe they come into fruition just now. So what I'll report on is the impact of artificial intelligence methods into overcoming the computational hurdles that stop us from making contact with particle physics, with real particle physics from string theory. So essentially what we try to do in string phenomenology is to explain the patterns that are observed in particle physics in terms of patterns that exist already in the fabric of space-time. So in the compactification data, in the topology and geometry of the extra dimensions which are predicted to exist by string theory. And the kind of patterns that I'm referring to, they're fundamental patterns, like why are there 3 generations of quarks and leptons, why the masses of particles span 6 orders of magnitude, and how to compute these masses from first principles. So these are fundamental questions, and as far as I know, string theory is the only framework in which such calculations can be done from first principles. So this is the standard model Lagrangian. This is the form that you like to print on a t-shirt or on a mug, but if you write it in its gory detail, this is maybe, I don't know, only a quarter of what it is. So there's a lot of detail there to capture. So string model building essentially goes in 3 steps. First, you want to construct models that have the correct gauge group and particle content. Then you want to compute Yukawa couplings, which tell you about the masses of quarks and leptons and the mixing parameters. And these will be functions of the moduli. So these will be functions of the parameters of the geometry. And finally, the third step is to stabilize the moduli and understand why do we observe the values that we observe for the masses and mixing parameters. So I'll be working in the context of the 8 times 8 heterotic string. And this involves the compactification from 10 dimensions to 4 dimensions, involves a 6-dimensional manifold, which is required to be Ricci flat, so Calabi-Yau, in order to preserve n=1 supersymmetry. It involves a holomorphic vector bundle, which, again, for the reason of preserving supersymmetry, needs to be polystable or satisfy these Hermitian-Yang-Mills equations. And the matter fields, they are in one-to-one correspondence with cohomology representatives, more precisely with harmonic representatives of cohomology groups. Okay, so some of these conditions, you can construct Calabi-Yau manifolds without knowing the metric. So there are topological conditions, like the vanishing of the first-term class, which tells you once you have that, you're guaranteed to have a Calabi-Yau manifold. But obtaining the metric is a harder problem. The same with these vector bundles. You can construct them, but actually finding the field strength on them is a harder problem. And the first step you can do without knowing explicitly the metric on the manifold and the connection on the bundle. To proceed to the second step, you need those. So I'll discuss mainly about the first 2 points, and I won't touch the third point in this talk. Okay, so here is an example. We love to look at examples. So, this is a manifold which is described as a hypersurface in 4 complex projective spaces of dimension 1. So it has 4 scalar parameters, and the bundle is written as a sum of line bundles. So this is the simplest situation where the bundle is split into line bundles. So every line bundle is specified by 4 integers corresponding to the 4 scalar parameters that the manifold has. So there are 5 line bundles for this vector bundle. Computing cohomologies of V and higher wedge powers of V gives the information about the spectrum. So this is one example where we can recover the exact spectrum of the standard model, of the supersymmetric standard model. These are multiplets written in SU5 GAT notation, but the SU5 GAT can be broken to the standard model. And this is the model where we computed Yukawa couplings, and this is what I'll discuss at the end of the talk. So in the first step, you compute cohomology, you find what the spectrum is. In the second step, you look at the operators in the superpotential. And there is an up Yukawa coupling of rank 2 in this model. So at perturbative level, it has rank 2. You can hope that at non-perturbative level, it will have rank 3. And down Yukawa couplings are vanishing perturbatively, and there are no lepton Yukawa couplings in this model. So this is just one example. But this is one of many. So my first point in this talk is to show that such examples where you recover the exact spectrum of the standard model can be obtained on demand now. So the situation about 10 years ago was that there were only a handful of models that recovered the correct spectrum of the standard model. In 2013, so about 10 years ago, we undertook a massive search, scanning essentially over some 10 to the 40 pairs of manifolds and bundles, and this resulted in several millions of models that have the correct particle spectrum. And more recently, we used heuristic searches, so genetic algorithms and reinforcement learning, to search even larger portions of the landscape, of the string landscape. So now we are at a point where models can be generated on demand. We don't let the computer run. I mean, if need be, we'll start the computer again. We have the methods, and if we need more models, we'll let the computer run for longer. So let me go back to this example. So the vector bundle, once you specify a manifold, the vector bundle is specified in terms of a bunch of integers. So those integers, adjusting those integers takes you from one model to another model. Right? So this is really a discrete optimization problem. And genetic algorithms seem to be doing very well in this situation, in this discrete optimization problem. So finding models that have the correct spectrum, at least at the level of having 3 generations of quarks and leptons, and satisfying other constraints like anomaly cancellation, can be phrased in terms of a set of Diophantine equations and inequalities. So you encode the integers that specify the bundle into sequences of into binary sequences. So this is what genetic algorithms are. You encode the data that specifies the problem into binary strings, and then you start with a population of random such binary strings. You rank them according to how well they solve the problem that you are specifying, and then you start breeding them and mutating them. Another method that we used was reinforcement learning, which has a very different philosophy. You have an agent which hops between different solutions, so there are different actions that it can perform, and it gets reward according to how, in a sequence of steps, if it encounters good solutions or not. And the policy, so the policy is what dictates in which direction to hop between these solutions, is controlled by a neural network. So this is a neural network approach. The other one genetic algorithms don't have this element of machine learning. It's a much older method, but both of them, in searching over huge spaces, they seem to land on the same models. So we looked at, so I have two lessons here. So first we made a comparison between systematic searches that we performed earlier and results obtained with GA and RL, and we obtained virtually the same results while scanning only a fraction of 10 to the minus 20. So this is quite surprising. You don't scan the full space, you scan a tiny fraction, 10 to the minus 20, and you obtain all the solutions. And you know that you found all the solutions because you performed already a systematic scan. You may wonder, how on earth can one scan things like 10 to the 40 solutions? We use some tricks. So in those systematic scans, we used some tricks which allowed us to scan over 10 to the 40 different pairs of manifolds and bundles. While here, in using genetic algorithms and reinforcement learning, we did not involve those tricks. Comparison between GA and RL, so they are very different philosophies, but they produce the same set of results, so that gives us an idea that we found all the models available. The second step is to actually look into more detail into the spectrum, so to actually see that if there is a Higgs particle, for instance, not only 3 generations of particles, but also a Higgs field. And this involves computations of cohomology. These are hugely expensive computations, usually. So for manifolds embedded in products of projective spaces or toric varieties, there are algorithmic techniques. So it can all be traced back to cohomologies on projective spaces for which there exist explicit formulae. And using exact sequences and spectral sequences, there is a whole technology which can be implemented, and we have implemented it into computer algebra packages. But still, so you don't have to do the calculations by hand, the computer does them for you. It takes a long time. So the computational cost is large, and often it hits the buffers. It's just impractical to wait for such computations to finish. So what we observed by doing many such computations, we observed certain patterns that line bundle cohomologies can be expressed in terms of simple formulae, which are locally polynomial formulae. There are, in this set of line bundles, there are different regions where these cohomologies can be expressed in terms of some polynomials. And this is something that we were not aware of, and as far as we know, it was not known in the mathematics literature either. Also, we know, so some of these observations were made directly by looking at data. Some of them were made using neural networks. So this is another place where artificial intelligence played a role in producing conjectures that this cohomology data can be reproduced by simple formulae. Once you have that hint, you can try to prove it, and we did that. We proved why these formulae arise. Moreover, there seem to be even simpler objects, like generating functions, which encode all the cohomology data of line bundles on given manifolds, on examples of manifolds. This is not a general result. It's just looking at different examples. We noticed that this is the case. So, of course, it's important for string model building to have such techniques which give virtually instantaneously the results that we are looking for. But also from an algebraic geometry point of view, especially these generating functions, they can be regarded as a fingerprint of the variety. So if you have an object which encodes the cohomology of all line bundles, so the zeros and the higher cohomologies, perhaps that's an object which uniquely characterizes the variety. So finally, let me quickly go to the computation of Yukawa couplings. You need two pieces to compute that. You need the holomorphic Yukawa couplings. So the nus are the harmonic forms which correspond to the matter fields. Omega is the top holomorphic form on the Calabi-Yau manifold. And you need also this matter field metric, which gives you the normalization of the matter fields if you want to write them in canonical form. So this Kij is computed as an integral. Again, you have the news, so these harmonic forms. You have the Hodge star operator, which involves the metric on the manifold. You have the bundle metric, so you need to have full knowledge of the manifold, of the bundle, and the harmonic forms on the these bundle valued harmonic forms. So these quantities, the holomorphic Yukawa couplings, you don't need the actual harmonic representatives. So they are quasi-topological quantities. However, for these normalization quantities, you need knowledge of everything. So computing the metric first, the Ricci flat metric, so you have the Ricci tensor equals to 0. This is a particularly bad equation. It's fourth order, if you write it in terms of a Kähler potential. A fourth order PDE, which is nonlinear, is particularly bad because the nonlinearities are in the highest derivatives. It's in 6 dimensions. It's as bad as it can get. So numerical methods are sort of hopeless on this problem. You can reformulate the problem in an easier form. So Yao wrote this condition, Ricci tensor equals to 0, in terms of a Monge-Ampere equation. So you have two quantities which give you the volume form on the manifold, so the wedge of omega and omega bar, and the Kähler form wedged with itself 3 times. You have a reference Kähler form which specifies the class where your manifold has a Kähler form, and then this del del bar phi term. And now the problem is to find phi, which is a globally defined real function, and it's a differential equation of order 2 only. So the technique that we used was to encode the solution, so this phi, as a neural network. The neural network is just a composition of linear functions and nonlinear functions, as Kostas was saying. It has parameters. You evaluate this equation. Let's say you evaluate this equation as the various points on the manifold, and you compute a loss function. Right, so this is the loss function, and that tells you how to change the parameters that specify phi. So you don't need to do finite steps anymore. You can solve these partial differential equations by modeling the function that you are looking for, phi, in terms of a neural network which has many tunable parameters. And of course you have, because you are on a manifold, you have to take care of transition losses. So these functions, they are on different patches, and you have to see what happens, what the gluing conditions are. So here, being just a function, the function has to be the same on the different patches. We did this on just a normal computer, so the training is not something that required supercomputers. And there is a similar story for the Hermitian-Young-Mills connection and for the harmonic forms. So in fact, this story about the metric has been done by various groups, and we used the techniques used in this paper, and we extended them for the Hermitian-Young-Mills connection and for the harmonic forms. A similar approach was undertaken by this group for standard embedding compactifications, where analytic results are also known, and the comparison between the two is spectacularly good. So this gives us confidence that these methods actually produce numerical results which are trustworthy. So the problem with the standard embedding is that you don't have models which produce the standard model particle content. That's why we need to go to these non-standard embedding models. And this is, in the model that I just presented at the beginning, this is an illustration of what the masses of the quarks turn out to be. So the mass of the top quark in particular, it should have been order 1, it's not order 1, so this is not a particularly realistic model, but it's just to show that these techniques work, and there is a huge set of models, millions of models on which these techniques can be applied. So let me stop here. Thank you very much.
Questions for Andrei?
Yes, please.
Thank you very much for the nice talk. I was wondering, so like 15 years ago, something like that, there was an attempt to do the approximation of Calabi-Why matrix, but with a traditional algorithm, I guess. And I've always wondered, this machine learning one, is it quicker or gives better results, or both, and by how much is the difference?
Yes. It is quicker indeed, on the one hand, so to train it's order of an hour, let's say, on a normal laptop. It's also that the dependence on the Kähler moduli is much easier to implement than with the Donaldson algorithm. So in that case, you have to rewrite the whole thing for different choices of the Kähler parameters. You have to write a different code, basically.
Thank you.
Thank you for the talk. I wanted to ask about 10 minus 20. So why it's so so good? So that you checked so small fraction. It means practically it means that they are organized in some, and they grouped right in some nice way.
It's completely unreasonable.
It's unreasonable. You don't have explanation for this, no?
I don't have an explanation, but indeed somehow this discrete optimization technique seems to have landed on a problem for which it is well adapted. So that there is a something like a theorem that if you try any optimization technique on all the problems, on all the optimization problems, on average they will do equally bad. And somehow the fact that it works in this case, it means that the problem is somehow adapted, but I can't put my finger on it to say what it is. Yeah.
Is there, so you said at the beginning that you will not talk about moduli stabilization. Is there anything that you can use ML to address moduli stabilization?
So the status of moduli stabilization is much better understood in type 2. In heterotic string, I think there is still work to be done, and we are working towards that, towards getting the heterotic string more or less on the same footing as type 2 moduli stabilization. And yes, once you are there, there are possibilities, but this is work in progress, so I didn't want to talk too much about it.
If there are no more questions, let's thank Andrei for a wonderful talk.